Continue on with homework 6. We're now looking at part 3, which is derive the expressions to calculate the ideal gas enthalpy for each species as a function of temperature, showing the ChemCAD expression for CP and integrating this from the standard state temperature 298.15 to the desired temperature T. We can use Wolfram alpha to show our integrations, and we want to compare our answer to the equation and CHE dot tools. So to find the enthalpy of an ideal gas, so HI, and then it's a function of temperature. It's dependent on temperature. And then since I is going to be the species, so it would be O2, N2, CH4, H2O, and CO2. So our enthalpy is going to be equal to our enthalpy of formation for each component, which is given at 298.15, plus the integral of the specific heat capacity in terms of the temperature. And our starting temperature is at 298.15, and we're going to our desired temperature of T. All right. So this is the expression that we want. Now we want to find the specific heat capacity, and that's when we use the ChemCAD equation. So ChemCAD equation 107 right here, and we see that A plus B times C over T over the hyperbolic sine of C over T squared plus D times E over T over the hyperbolic cosine of E over T squared. So our specific heat capacity equals this equation right here. So we want to integrate equation 107, and to do that we're going to use Wolfram alpha to do that. So we have the integral of C over T over the hyperbolic sine of C over T, and then all this squared, and then we want to integrate in terms of T. So when we look at this integration, we get that it equals C times the hyperbolic cotangent of C over T. And as you know, hyperbolic cotangent is the inverse of hyperbolic tangent. So now let's integrate the next one. So E over T, and then hyperbolic cosine. And when we integrate this part of the expression, we get negative E hyperbolic tan of E over T. So going back to our equation, let us replace the CP with our expression. So CP is going to equal, or the integral of CP is going to equal A times T plus B times C hyperbolic cotangent of C over T minus, because of that minus in the integral, D times E hyperbolic tangent of E over T. And we have 2 5 and T. So that is our expression to find our enthalpy of an ideal gas. And now we want to compare that to the che.tools equation. So if we come here, we look at our che.tools. Right here, you can see we have, this is the formula for the specific heat capacity. See, we have A plus B times C over T over the hyperbolic sine of C over T squared plus D times E over T over the hyperbolic cosine of E over T squared. And then if we come down here, here we find the equation we're looking for. So we have A times T plus B times C, and then it's the hyperbolic tangent of C over T. And we had our C over the hyperbolic tangent of C over T, which is equal to C times the hyperbolic cotangent of C over T, because cotangent is 1 over tangent. So we just move that to the bottom, make hyperbolic tan. And then minus our D times E times hyperbolic tangent of T over E. And then that divide by 1,000 is what I'm assuming is something for units. And that is how we get the equation for our ideal gas, the enthalpy. Yeah.